Ancient Rome delivered more water per citizen than the city does today, and they did it all without a single pump. This civilization mastered water on a scale that still inspires modern engineers. We see the grand stone arches, but the true marvel is the hidden science, the precise mathematics, and revolutionary materials that made these structures last for centuries. By the end of this exploration, you will understand the remarkable engineering insights that make Roman aqueducts a benchmark for sustainable design. How did they maintain a perfect water flow across dozens of miles using only gravity? What was the special ingredient in their concrete that gave it such lasting strength? The answers reveal a technological triumph whose lessons are only now being fully appreciated. What do you believe is the most important quality for an invention to stand the test of time? Rome's thirst for clean water was a matter of survival. The city's local springs and the Tiber River could no longer support its exploding population, and the resulting water scarcity created immense hardship. Illness spread easily, and the threat of social instability grew with each passing season. This crisis demanded a revolutionary answer, and it arrived in the form of the Aqua Appia. Commissioned by the censor Appius Claudius Caecus in 312 BC, this first aqueduct was a marvel of pragmatic design. It did not march across the landscape on towering arches, as later ones would. Instead, it was a hidden masterpiece, a deep tunnel carved through rock and earth, stretching for over 10 miles to bring fresh water from distant springs directly into the city's heart. This was more than an engineering project. It was a profound declaration. Appius Claudius used this monumental undertaking to cement his political legacy, demonstrating that Roman ambition could literally redirect nature to serve its people. The Aqua Appia did not just deliver water, it delivered a new vision for urban life, proving that a state's strength was measured by its ability to provide for the health and prosperity of its citizens. The success of this single, underground channel ignited a building frenzy that would eventually weave a network of aqueducts across the entire empire, creating a hydraulic backbone for a civilization destined to endure for centuries. The success of Rome's first aqueduct did not come from brute force but from brilliant foresight. Before any grand arches could rise, a different kind of hero took the stage, the agrimensors. These master surveyors were the true architects of the aqueducts, and their work began with a seemingly impossible question. How do you make water run downhill for 50 miles when the hill itself is barely perceptible to the human eye? Their toolkit was deceptively simple. The groma, a clever cross of wooden arms with weighted plumb lines, allowed them to trace perfectly straight paths across the landscape, the foundation for their entire route. But their most vital instrument was the chorobates. Imagine a wooden bench nearly 20 feet long with a carefully carved channel running along its top. By filling this groove with water and observing its surface, the surveyors had a level of such sensitivity it could detect a slope of just 1 part in 2,000. This meant over a mile the channel could drop by only 2.5 feet, and they would know it. Such precision is difficult to achieve even with modern technology. Yet these engineers worked without it, facing the Earth's subtle curve and the relentless challenge of Italy's rugged terrain. They had to predict how spring floods and summer droughts would affect their water source, planning for a flow that would remain consistent through every season. This was engineering as an act of profound patience. A single miscalculation, a gradient a fraction too steep or too shallow, and the entire project would falter. The water would either rush forth with overwhelming force, wearing down the channel walls, or it would settle into a still, muddy pool. The true marvel is that they almost never got it wrong. Their calculations, etched into wax tablets and scrolls long before the first shovels struck earth, were the invisible blueprint for an empire's thirst. This was the hidden genesis of every aqueduct, a testament to the power of a plan so meticulous it could persuade a river to walk. That meticulous planning on the wax tablets set in motion a force of nature itself. The entire Roman aqueduct system was a gravity-driven superhighway, a masterpiece of motion without a single moving part. Water began its journey high in the mountains, at a spring source that sat well above the ultimate destination of the city. From that high point it was all downhill, a slow and deliberate descent orchestrated by that minuscule, precisely calculated gradient. This was not a rushing river. The channel was designed to drop only a few centimeters for every 100 meters it traveled, a slope so gentle you would scarcely notice it while walking alongside it. This barely perceptible decline was the system's genius. It created a flow that was steady and constant, powerful enough to keep the water moving for dozens of miles, yet gentle enough that it would not scour or wear down the delicate channel walls over centuries of use. Think of tilting a dinner plate just enough for a trickle of water to glide from the center to the edge, never pooling, never rushing, just moving with a quiet, persistent purpose. That is the elegance the Roman engineers achieved on an imperial scale. This simple reliance on gravity, a fundamental force they could not create but could brilliantly harness, made the network profoundly resilient. There were no pumps to brake, no engines to fuel. Once the water was released at the source, nature itself took over the work of delivery. This stands in stark contrast to so much of our modern infrastructure, which requires constant energy input and complex machinery. The Romans built a system that was, in its very principle, low maintenance and sustainable. This core philosophy of working with physics, not against it, would be echoed in the very stuff they built with, the revolutionary concrete that gave these structures their legendary endurance. Yet the true genius of the aqueducts lies not in what was seen, but in what remained hidden from view. For every mile of soaring stone arches that captured the public imagination, nearly 5 miles of the system ran silently underground. This was the empire's secret circulatory system, a labyrinth of tunnels and covered trenches carved through the living rock. By placing the vast majority of their water channels below the surface, Roman engineers solved a host of problems with one elegant solution. The subterranean stone shielded the precious flow from the scorching sun, drastically reducing evaporation. It kept the water refreshingly cool and sealed away from the open air, protected it from dust, debris, and contamination. In an age of frequent conflict, this hidden network was also a strategic masterstroke, making the city's water supply nearly invulnerable to disruption by an opposing force. But perhaps the most compelling reason was sheer economics. Building a continuous elevated channel across every hill and valley was a monumental and costly endeavor. It was far more efficient to simply go through an obstacle than to meticulously bridge over it. Teams of laborers and miners would tunnel straight through the hearts of mountains, their work illuminated by flickering oil lamps. These channels were then lined with that miraculous, waterproof Roman concrete, creating a smooth, durable conduit. This overwhelming preference for the hidden path reveals a core tenet of Roman engineering philosophy, a deep-seated pragmatism that prized long-term function over fleeting spectacle. They invested their greatest efforts and their most advanced materials not in the showy arches, but in the dark, silent tunnels that guaranteed the system's endurance for centuries. And the key to that endurance, the magical property of their concrete, was a secret ingredient so potent it could only be born from a remarkable natural event. The long-lasting strength of Roman concrete came not from magic but from a remarkable volcanic gift. The Romans discovered that a specific ash mined from regions like Pozzuoli near Mount Vesuvius held a secret power. They called this material pozzolana, and when they mixed it with lime and water, it created a chemical reaction that defied the understanding of the ancient world. This was no ordinary mortar. It was a hydraulic concrete, meaning it could set and harden even when completely submerged in water, a property absolutely essential for lining aqueduct channels and building the foundations of bridges that stood in rivers. But its most astonishing feature was its behavior over centuries. While modern concrete structures can show their age within decades, Roman concrete seemed to possess a form of life. Tiny, latent crystals within the pozzolana mixture would slowly react with mineral-rich water seeping through microscopic cracks. This ongoing process, a recrystallization, would actually fill and seal those fissures from the inside out. The material did not just resist decay, it actively fought it, growing more resilient with the passage of time. This self-healing ability is something modern material scientists are only now learning to replicate. The Romans, with no knowledge of complex chemistry, achieved this by being brilliant observers of their natural world. They saw the unique properties of this volcanic soil and harnessed them on an imperial scale. This concrete became the invisible armor of their water network, lining every underground tunnel and forming the core of every massive pier that supported the elevated sections. It was this local, almost miraculous resource, transformed by human ingenuity, that allowed their aqueducts to not just be built but to endure, and this incredible delivery system, once it reached the city, faced its final and most critical test, the challenge of making the water safe for 1 million people to drink. When the subterranean channels met a wide valley, Roman engineering rose to the occasion quite literally. The solution was the arcade, a marching sequence of stone arches that has become the defining image of their hydraulic genius. But these structures were far more than beautiful monuments. Each semicircular arch was a masterclass in physics, a shape perfectly designed to channel immense forces. The weight of the entire water channel, along with the stonework itself, was not simply dropped downward. The arch cleverly transformed that vertical load into outward thrust, pushing against its neighboring arches. This mutual support created a stable, interlocking system where the forces were efficiently shunted down through the sturdy piers and deep into the ground. This principle allowed the Romans to build breathtakingly high and long aqueducts using far less stone than a solid wall would require. It was an exercise in elegant efficiency. This brilliance extended to their construction methods. The arches were modular, built from precisely cut stone blocks that could be shaped in quarries far from the final site. Think of it like assembling a massive, weight-bearing puzzle from pre-made pieces. This standardization dramatically sped up the building process, allowing crews to work on multiple sections of an arcade simultaneously. The result was structures like the Pont du Gard in southern France, a triple-tiered arcade that strides across a river valley. It is impossible to stand before it and not feel a sense of awe, not just for its scale, but for its perfect harmony. Every line, every curve serves a clear structural purpose, yet the overall effect is one of breathtaking beauty. It is a bridge that does not just cross a gap, it proclaims the power of an empire that could bring order and grace to any landscape. This fusion of raw utility and artistic statement is what separates Roman work from mere construction. But even these monumental arches were only one part of a much larger, living system that required constant, attentive care to function for centuries. Flowing through the very center of those grand arches and silent tunnels was the Specus, the aqueduct's true heart. This was not a simple ditch for water. It was a meticulously crafted enclosed conduit, a custom-built environment designed for one purpose: to deliver water with perfect efficiency. The channel was typically rectangular or U-shaped, lined with that same waterproof Roman concrete to create a surface as smooth as glass. This smoothness was not a luxury. It was a critical engineering choice to minimize friction. By reducing the drag against the channel walls, the water could maintain its velocity and travel far greater distances without slowing to a stagnant crawl. Every curve and dimension of the Specus was precisely calculated based on the volume of water expected from the source springs and the projected demand of the city it served. A channel too wide would cause the flow to become shallow and sluggish, while one too narrow would create dangerous pressure and risk overflow. To complete the system, these channels were often sealed with heavy stone slabs. This covering served a dual purpose. It blocked sunlight, preventing the growth of algae and bacteria that could affect the supply, and it acted as a physical shield, keeping out leaves, animals, and wind-blown debris. This obsessive attention to the micro-details of the water's journey reveals a profound truth about Roman engineering. Their genius was not confined to the monumental scale of arches that stretched across valleys. It was equally present in the intimate, hidden space where the water actually flowed. They understood that the grandest structure would fail if the final foot of its journey was not perfected. The Specus was the culmination of that philosophy, a testament to the power of perfecting the small, unseen details to achieve a monumental result. And once this perfectly channeled water reached the bustling city, it faced a new challenge: how to be fairly and cleanly distributed to every corner of Roman society. This clear, gently flowing water was not a lucky accident. It was the final achievement of a system designed for purity. Before a single drop from the aqueduct entered the bustling city, it was ushered into a series of vast, quiet pools known as piscinae limeriae, the settling tanks. Here, the aqueduct's steady current met a sudden, deliberate calm. The water would spread out across these wide basins, its speed dropping to almost nothing. In this new stillness, gravity could perform its most basic yet vital task. Invisible particles of silt, fine sand, and other natural material, which had been carried along for miles, suddenly lost their momentum. They drifted slowly downward, settling as a soft layer on the smooth tank floor. The water left behind was transformed, noticeably clearer and free of the grit that could affect both its safety and its taste. This was not a one-time process. The Romans designed these tanks with remarkable foresight, incorporating access points and sluice gates. Maintenance crews could periodically enter and clear out the accumulated material, a routine cleaning that guaranteed the system's long-term effectiveness. This simple act of letting water rest before its final journey was a profound public health innovation. It represents one of the earliest and most sophisticated applications of water treatment, a principle that remains the very first step in modern purification plants today. This commitment to clarity reveals that Roman engineering was not solely about quantity, but deeply concerned with the quality of life it supported. After this crucial cleansing pause, the water was finally ready for its most complex challenge, entering the city to navigate a labyrinth of law, privilege, and public need. The journey of the water did not end with its arrival at the city walls. It arrived at a final, critical junction, a distribution fortress known as the Castellum Divisorium. This large, circular tank was the grand terminal where the single, powerful stream from the aqueduct was tamed and divided. Here, the water's purpose was redefined, transforming from a simple delivery into a complex act of civic management. The design was a masterpiece of practical intelligence. Multiple outlets positioned at different heights on the tank's walls fed a network of smaller lead or ceramic pipes. Each pipe was a dedicated path carrying water to a specific part of the urban landscape. The highest priority was given to the people. The primary and largest outflows were reserved for public needs, channeling fresh water to the bustling street fountains, the vast public baths, and the essential public latrines. This ensured that the core services supporting public health and daily life would never run dry. Only after these public needs were met would secondary lines supply water to private residences, workshops, and the villas of the wealthy. This was not a random division. It was a deliberate, legally enforced system of prioritization. The architecture of the castellum itself guaranteed this hierarchy. If the water level in the tank ever dropped due to a seasonal shortage or a problem upstream, the lower, private outlets would be the first to run dry. The public fountains, fed from the highest outlets, would continue to flow. This brilliant design created a resilient water grid, an early and sophisticated model of urban resource management that balanced communal need with private access. It was a physical expression of a social promise, ensuring that the city's lifeblood reached everyone. But this intricate network of pipes snaking beneath the city streets now carried its own complex story, one that would be discussed for 2,000 years. The constant murmur of flowing water was the heartbeat of ancient Rome, a sound most familiar at the street corner Lacus. These public fountains were far more than simple stone basins. They were the ultimate expression of the aqueduct's purpose, transforming engineering into an act of daily generosity. For the overwhelming majority of Rome's population, from shopkeepers and laborers to the residents of its towering apartment blocks, the Lacus was the only source of drinking water. Their homes had no private taps. This was not a failure of the system, but its core design. By placing these fountains at nearly every major crossroads, the Roman state guaranteed that no citizen, regardless of their status, had to walk more than a short distance for a necessity of life. The water was provided free of charge, a powerful statement in a society with deep social divisions. Here at the Lacus, everyone stood on equal footing, sharing in the same clean, cold water that had traveled dozens of miles from the mountains. The social role of these fountains cannot be overstated. They were natural gathering points, places where news was exchanged and the pulse of the neighborhood was taken. This daily ritual of collection fostered a powerful sense of community, binding the city together around a shared public resource. But the fountain's utility extended far beyond quenching thirst. Its overflow was never wasted. The water that spilled continuously from the basin was channeled directly into the gutters, where it performed a critical secondary function. This steady stream helped clear the streets, carrying material toward the city's vast sewer network. This simple, elegant design linked public health directly to public access, using the same water to sustain life and to maintain cleanliness. The Lacus was therefore a perfect symbol of Roman civic philosophy, a tangible demonstration that the state's strength was measured by its ability to care for the collective well-being of its people. But this public water supply also fueled the most ambitious social experiment of the ancient world, the Imperial bathhouses. To step into the baths of Caracalla was to enter a universe of water. This was not a single building but a sprawling city within a city, a palace of public leisure that could welcome thousands of citizens at a time. Its existence was a direct consequence of the aqueducts, a voracious consumer of the clear, cold mountain water flowing into Rome. The scale of its thirst is almost beyond comprehension. Every single day, the complex required a volume of water that would fill several Olympic-sized swimming pools. This colossal supply did far more than fill the vast swimming pool, or natatio. It circulated through a sophisticated thermal circuit. A continuous flow fed the searingly hot caldarium, where steam billowed from heated pools and then replenished the shocking chill of the frigidarium for the traditional cold plunge. Most impressively, this water was the lifeblood of the hypocaust, the revolutionary underfloor heating system. Beneath the ornate marble floors, a maze of brick pillars created a hidden space where hot air from furnaces circulated, warming the rooms above. But these furnaces did more than heat air. They also heated water in large bronze boilers, creating the steam and hot water that fed the entire complex. Managing this hydrological cycle, this constant flow of hot and cold, clean and used water, was a logistical ballet of staggering complexity. The imperial baths were therefore the ultimate expression of hydraulic power. They demonstrated that the state could command not just the basics of survival, but the very pinnacle of comfort and leisure, delivering it on a mass scale. By making this luxury accessible for a minimal fee to every strata of Roman society, the baths became a powerful tool of political messaging. They were a physical, daily reminder that the peace and prosperity of the empire flowed as reliably as the water in its pools. This culture of public luxury, however, had a private counterpart, one that revealed a different side of the Roman relationship with water. While the public fountains served the many, the ultimate luxury was a whisper of water within one's own walls. For the elite of Rome, the true measure of status was not just wealth, but a private connection to the aqueduct itself. This was not a simple matter of running a pipe. Obtaining this privilege required a special license from the emperor or the senate, a formal grant that always came with a substantial payment to the state. This process transformed running water from a public resource into a powerful symbol of personal influence. Inside a wealthy citizen's domus, this private access enabled a level of comfort that rivaled the public baths. Water piped directly into the home could feed a small, private bath suite, a profound luxury in a crowded city. It supplied kitchens and latrines, and most conspicuously, it fed ornate marble fountains that bubbled at the center of shaded courtyards. The constant, gentle sound of this water was a deliberate display, an auditory announcement of the owner's privileged position. This created a complex duality within the water system. The same network that guaranteed a free, clean supply for every citizen at the street corner also served to reinforce the very social hierarchies that defined Roman life. The public aqueduct was a great equalizer in its primary function, but its secondary, private distribution was a tool of distinction. It illustrated a nuanced balance, a society that could provide for the collective welfare while simultaneously catering to the desires of the powerful. This interplay between public good and private privilege was engineered into the system itself, a quiet testament to the fact that even water, the most essential of resources, could be channeled to reflect the structure of the society it served. But the grand arches and hidden channels were only half the story. The true endurance of the aqueducts came from a relentless, quiet effort that unfolded every single day. This was not a system you could simply build and abandon. It demanded a sophisticated, state-funded maintenance regime, a form of perpetual care that was as brilliant as the initial design. This vital work fell to the aquarii, specialized teams of workers who served as the aqueduct's dedicated guardians. Their task was constant and methodical. They patrolled the entire network, walking the elevated arcades and descending into the dark tunnels through access shafts known as puttae. These regularly spaced openings were the system's service doors, allowing the aquarii to reach the channel below for inspection and cleaning. Their work was gritty and essential. They carefully removed stubborn mineral deposits that could slowly reduce the water's flow. They cleared out invading plant roots that sought out the constant moisture, and they repaired any fine cracks in the concrete lining before they could widen. They also ensured the settling tanks were regularly cleared, maintaining their crucial clarifying power. This was a proactive, not a reactive, approach to upkeep. The Romans understood that a small, regular repair was infinitely more manageable than a major failure. This long-term operational mindset, this commitment to stewardship over centuries, is perhaps one of their most profound legacies. It demonstrates that the greatest engineering is not just about creating a marvel, but about nurturing it, ensuring that the initial spark of genius continues to serve generation after generation. Yet for all its hydraulic brilliance, the aqueduct network would have been meaningless without the rule of law. A system this vast, serving a city of 1 million people, required more than concrete and gravity. It demanded a robust legal and administrative framework to prevent it from descending into chaos. This responsibility fell to a unique figure, the curator aquarum. This was no minor bureaucrat. The curator was a high-ranking senator, a man of immense political standing personally appointed by the emperor. His authority extended over the entire water supply, from the mountain springs to the final distribution tank. He managed the budget, oversaw the legions of maintenance workers, and possessed the legal power to enforce the intricate rules governing every drop of water. This elevated appointment sent a clear message. The integrity of the water supply was a matter of state security, as vital as the army or the treasury. We know the inner workings of this system in remarkable detail thanks to one such curator, Sextus Julius Frontinus. After his appointment in the late 1st century, he wrote a meticulous report, De Aqueductu, a document that reads like a modern operations manual. In it, he details the precise legal dimensions for the lead pipes used for private connections, the exact penalties for illegally tapping the public supply, and the strict protocols for maintaining purity. Diverting water without permission was a serious offense, treated not as a minor violation but as a direct challenge to the common welfare. The laws were unequivocal. The primary flow was reserved for the people, for their drinking fountains and their baths. Private users who paid for the privilege received only what remained after public needs were fully satisfied. This legal framework transformed the aqueducts from a marvel of engineering into a lasting civic institution. It proved that the Romans understood a profound and timeless truth. The most brilliant technology is only as strong as the social contract that protects it. A perfect channel means nothing if the water within it can be taken improperly or compromised. By building a legal system as resilient as their arches, they ensured their engineering would serve not just a generation, but the centuries to come. This mastery of water extended far beyond city fountains and public baths, into the raw industrial landscape of the mines. In the hills of Roman Spain, the same principles that delivered life to a metropolis were harnessed for a completely different purpose, the systematic reshaping of the land itself. Here, aqueducts were not civic amenities, they were the engines of a massive industrial enterprise. Engineers constructed elaborate channel systems to divert entire rivers, carrying colossal volumes of water to artificial reservoirs perched high on gold-rich mountains. The true application of this power was a technique known as hushing. It began with a tense, controlled silence as millions of gallons of water were held back by timber and earthen dams. Then, on command, the barriers were released. The result was not a gentle flow, but a calculated, overwhelming surge. This unleashed torrent would thunder down the mountainside with the force of a natural event, deliberately clearing away soil, trees, and entire layers of rock. In moments, what was once a wooded hill slope was transformed, leaving the precious gold-bearing ore beneath exposed for teams of workers to process. This was hydraulic engineering transformed into a tool of pure extraction, a display of power so immense it could literally reshape geography for economic gain. The Roman aqueduct, a symbol of urban order and public health, revealed another face in the mines, that of a disciplined and potent force. This application proves the profound versatility of their vision. They saw water not just as a sustainer of life, but as a fluid instrument of power, an agent of economic might that could be directed with the same precision they used to fill a public fountain. It was a clear demonstration that their control over nature was absolute, serving the needs of the community with one hand and the relentless demands of the empire with the other. The fading of the Roman world did not shatter its aqueducts, but it did fracture the knowledge required to build them. For centuries, the great arcades stood as silent, skeletal monuments to a forgotten science. Across Western Europe, large-scale urban water systems became a memory. Societies returned to a local rhythm of life, drawing water from wells and nearby rivers, their horizons and their engineering ambitions shrinking accordingly. The magnificent Roman channels, no longer maintained by the legions of aquarii, slowly succumbed to time. Their smooth concrete linings cracked, their channels filled with soil and roots, and their grand stone blocks were carefully taken away piece by piece to build city walls, churches, and castles. The aqueducts were being dismantled not by conquest, but by the pragmatic needs of a new age that saw them not as a system, but as a convenient quarry. Yet their physical presence never faded. These colossal ruins marching across the countryside remained a constant and humbling presence in the medieval landscape. They were a tangible mystery, a stone puzzle that whispered of an era when human ambition operated on a different scale entirely. They stood as a challenge, a question written in arches and mortar, waiting for a time when people would once again dare to ask how such things were possible. That time of reawakening arrived with the Renaissance, a renewed fascination with classical texts and a spirit of empirical inquiry turned artists and thinkers into detectives of the past. Leonardo da Vinci, driven by an insatiable curiosity for both art and mechanics, meticulously studied the broken traces of Roman hydraulics. His notebooks are filled with intricate sketches of valves, sluice gates, and siphon systems, direct attempts to decode the engineering principles that made the ancient network flow. He was not alone. This revival of classical learning rekindled the very Roman idea that a state's greatness was measured by its public works. The crumbling aqueducts were no longer just ghosts of a lost empire, they were textbooks. They offered profound lessons in civic planning, structural integrity, and the harnessing of natural forces. The ambition to once again provide clean water for growing cities began to stir, planting the essential seeds from which the entire field of modern civil engineering would eventually grow. This silent, steady flow was a mathematical symphony. The water did not just run downhill, it followed a precise equation, one that Roman engineers had internalized through generations of observation and refinement. They understood the invisible relationships governing moving water, the interplay between the channel's shape, the friction along its walls, and the gentle pull of its slope. Their genius lay in translating this complex physics into simple, workable rules. A key concept was the cross-sectional area of the channel, the size of the pipe through which the water traveled. They knew that a wider channel could carry more water, but only to a point. If it was too wide for the volume of water available, the flow would become shallow and sluggish, losing the energy needed for its long journey. They also paid meticulous attention to the wetted perimeter, the total length of the channel's sides and floor that were in contact with the water. A smoother surface and a more efficient shape, like a semicircle, minimized this contact, reducing the friction that would slow the water down. All of this was balanced against the gradient, that barely perceptible slope they measured with the chorobates. Too steep, and the water would rush forward, risking damage to the channel. Too shallow and it would stagnate. They were solving for a single perfect variable, the flow rate, ensuring that a consistent volume of water arrived at the city gates every single hour. This was not abstract calculus, it was a deeply practical mathematics, a set of proportions and ratios recorded in manuals and passed down through apprenticeships. The architect Vitruvius codified many of these principles, providing standardized dimensions for channels based on the capacity of their water source. This empirical knowledge meant that an engineer in Gaul could build a channel with the same confident precision as one in North Africa, creating a predictable and reliable system across the entire empire. The ultimate proof of their calculations was not on their wax tablets, but in the performance of the water itself. When it arrived in the city after a journey of 50 miles, it still possessed enough residual force, enough living pressure, to leap from a public fountain or to efficiently serve the public latrines. That final, energetic splash was the quiet testament to a computational skill that shaped an empire's destiny. That final energetic splash was a testament to more than just mathematics. It was proof of a profound partnership with the land itself. Roman engineers were not just builders, they were master readers of the natural world, possessing an environmental acumen that guided their every decision long before the first stone was laid. Their primary goal was to find the purest water possible, and for that, they sought out specific geological formations. They knew that springs emerging from limestone or volcanic aquifers offered a superior source. As rainwater percolated slowly through these porous rocks, it underwent a natural filtration process. The stone acted like a massive subterranean sieve, straining out impurities and sediment, delivering water that was not only clear but also consistently cool and rich in beneficial minerals. This was not a happy accident. It was a deliberate targeting of nature's own purification systems. This deep geological understanding extended to the challenging work of tunneling. When an aqueduct's path demanded going straight through a mountain, surveyors chose their route with incredible care. They identified and followed layers of stable, solid rock, skillfully avoiding zones of loose material or geological weaknesses that could lead to instability. This careful selection minimized the risk during construction and ensured the tunnel would remain secure for centuries. The entire route of an aqueduct, therefore, was a masterclass in working with the landscape's grain. Engineers would trace a path that used natural contours to their advantage, weaving through valleys and riding ridgelines to maintain that crucial, gentle gradient with the least amount of disruptive excavation or expensive bridging. This was not a war against nature, but a form of collaboration. They listened to the lay of the land, and in return, the land provided a stable foundation and a pristine resource. This symbiotic relationship, this respect for the forces of geology and hydrology, is a fundamental reason why these structures have withstood earthquakes, floods, and the relentless passage of 2,000 years. They were built not just on the earth, but in harmony with it. The staggering cost of an aqueduct required an empire's treasury to fund it. These monumental projects were not paid for by local taxes alone, but by the colossal wealth flowing into Rome from its vast dominions. A significant portion of the funding came directly from the resources acquired during military campaigns, the gold and silver gathered from distant kingdoms. Emperors and powerful senators also frequently financed new aqueducts or major repairs from their personal fortunes, viewing such public works as the ultimate way to secure their legacy and popular support. This was far more than simple spending. It was a profound and calculated investment in the empire's very foundation. By guaranteeing a clean, abundant water supply, the state enabled its capital city to sustain a population that would eventually swell to over 1 million people. This massive, concentrated population was not a burden. It was the engine of the Roman economy. A constant stream of water powered essential industries that defined urban life. The distinct sense of tanneries, where animal hides were transformed into leather, depended on vast quantities of water for soaking and cleaning. The bustling fulleries, where wool was cleaned and thickened, required endless flows for washing and rinsing cloth. These water-intensive operations could never have existed on such a scale without the aqueducts. They provided jobs, produced essential goods, and fueled commerce across the Mediterranean. The water flowing through the arches was, in a very real sense, also flowing into the state's financial strength. It supported the legions by supplying the cities that produced their equipment and paid their taxes. It created the stable, prosperous conditions that allowed trade to flourish. The initial outlay of gold and silver was returned many times over through economic growth and social stability. The aqueduct was not a drain on the empire's resources. It was one of its most powerful economic engines, a machine built not of gears, but of gravity and water, generating wealth for centuries. The shadow of Roman engineering stretched far beyond the legions and the imperial frontiers. As the empire's influence rippled outward, so too did the core principles of its hydraulic science, often carried by the very engineers and traders who traveled its roads. In the arid landscapes of the Middle East, Byzantine and later Islamic builders looked upon the Roman model not as a final word, but as a brilliant starting point. They absorbed the concepts of the gravity-fed channel and the arch, then refined them for their own unique environments and needs. This was not mere copying, it was a process of creative adaptation. While Roman aqueducts often marched across the surface, these cultures perfected the canat, a subterranean water channel that tapped into mountain water sources. A primary well was dug deep into the water table, and from its base a gently sloping tunnel was carved for miles, allowing groundwater to flow freely to the surface at a lower elevation, all without a single pump. This was a different answer to the same fundamental question the Romans had asked: how do you sustain a civilization with a reliable water supply? It proved the adaptability of the core Roman insight, that water could be persuaded to travel great distances through careful planning and a deep understanding of natural slopes. Remarkably, on the other side of the world, entirely separate from Roman influence, other civilizations arrived at a similar conclusion. The Maya in Mesoamerica and the Inca in the Andes faced their own water challenges, from seasonal dry periods to steep mountain terrain. Their response was a parallel innovation that feels strikingly familiar. The Maya constructed intricate networks of canals and reservoirs to capture rainwater and manage it through the dry seasons, supporting their vast city-states. High in the Andes, the Inca engineered breathtaking terraces that cascaded down mountainsides. These were not just agricultural plots, they were sophisticated hydrological tools. A complex system of stone channels directed water from high-altitude springs to irrigate each level, controlling erosion and creating microclimates for growing crops. The water flowed entirely by gravity, a principle the Inca understood as intimately as any Roman surveyor with his leveling instrument. This global perspective reveals a profound truth. The drive to harness water is a universal thread in the story of human civilization. From the Khanats of Persia to the terraces of Machu Picchu, communities separated by oceans and millennia were all solving the same essential puzzle. The Roman aqueduct stands out not because it was unique in its ambition, but because it represents one of the most systematic, scalable, and enduring expressions of that universal human imperative. It reminds us that the greatest engineering challenges are often the most fundamental, and the solutions, though varied in form, are often united by a simple, powerful logic. For centuries, the secret of Roman concrete was locked within its own enduring strength. Modern scientists could see the results: aqueducts that stood for 2,000 years while some of our own structures weaken in just decades, but they could not explain the chemistry. The mystery was a profound puzzle, one that required tools the Romans never had to finally solve. Researchers turned powerful electron microscopes onto tiny samples of the ancient material, peering into its molecular heart. What they found was a stunningly complex and active world. The key was not just the pozzolana ash, but a specific, rare mineral that formed within the mix, a luminous tobamorite. This crystal is incredibly strong and typically only forms in the intense heat of a volcano, not in a man-made mixture at room temperature. Yet there it was, woven throughout the Roman concrete, reinforcing it like microscopic steel rebar. The second discovery was even more remarkable. Scientists analyzing Roman harbor walls that had been submerged in seawater for millennia found that the salt water was not degrading the concrete. It was actually repairing it. The water slowly reacted with the volcanic ash and lime, prompting the growth of new, interlocking crystals that seamlessly filled any tiny cracks that formed over time. This concrete did not just resist decay, it possessed a form of self-healing. This revelation is far more than a historical footnote. It is actively reshaping modern materials science. Engineers and chemists are now working to reverse engineer this ancient recipe, creating new, green concretes that are far more durable and require less energy to produce. The goal is to build seawalls, foundations, and infrastructure that can last for centuries, not just decades, and to do so with a smaller environmental footprint. The silent, stoic arches of the Roman aqueducts have finally begun to whisper their greatest secret, offering a lesson from the past that is guiding the sustainable building practices of our future. That final whisper from the ancient concrete carries a challenging question for our own modern world. Our water systems are a miracle of pressurized convenience, capable of sending water shooting up to the top of a skyscraper with a simple turn of a handle, a feat that would have astounded a Roman engineer. This power comes from a vast, interconnected network of electrically powered pumps, advanced filtration plants, and complex computer controls. We have traded the Roman reliance on gravity for a reliance on something far more volatile, a constant and uninterrupted supply of energy. This fundamental difference creates a hidden fragility. Our pressurized pipes can deliver immense force, but they are also under immense stress, vulnerable to a single point of failure. A major power outage, a cyber incident, or the failure of a key pumping station can disrupt the flow for millions of people in an instant, demonstrating how our complex web of efficiency can become a cascade of vulnerability. The Roman system could never send water to a 20th floor apartment, but its elegant simplicity was its greatest armor. It was a passive network, a machine with no moving parts to break, no external power to fail. Once the water entered the channel, nature itself became the perpetual engine. This comparison is not about declaring one system superior, but about understanding a critical trade-off. We have prioritized immediate power and pinpoint control, but have we sacrificed the robust, self-healing resilience that allowed Roman aqueducts to outlive empires? Their engineering philosophy asked a different question: not how much force can we create, but how much can we accomplish with the forces that are already freely and reliably given. In an era of increasing environmental and social uncertainty, their 2,000-year-old lesson in sustainable design feels more urgent than ever, inviting us to reconsider the very foundations of how we build our world. The Roman aqueduct stands as a timeless masterclass in sustainable design, offering a blueprint we are only now relearning. Their approach began with the ground beneath their feet. They did not import exotic materials across continents. Instead, they maximized local stone, earth, and that remarkable volcanic ash, pozzolana. This was not just a matter of convenience. It created a closed-loop system where the energy and environmental cost of transportation was minimized, and the materials were perfectly adapted to the local climate and geology. This principle of local sourcing is a cornerstone of modern green building, a direct echo of Roman pragmatism. Their entire system ran on a single, inexhaustible power source, gravity. This passive energy design required no fuel, emitted no waste, and could not be switched off. Once the water was set in motion, nature itself became the perpetual, silent engine. Compare this to the vast amounts of electricity our modern water systems consume for pumping and treatment. The Roman model asks a profound question. How much can we accomplish by working with natural forces, rather than constantly fighting against them with complex technology? But perhaps their most radical commitment was to time itself. They did not build for a decade or even a century. They built for millennia, designing durability directly into the fabric of their structures. They accepted higher initial costs, knowing they would be spread over 1,000 years of service. This long-term perspective stands in stark contrast to the short economic cycles that often guide our infrastructure projects today. Finally, their system was architecturally designed for fairness. The tiered distribution from the Castellum Divisorium legally guaranteed that public needs were met first, creating a resilient and equitable social framework. The aqueduct was not a tool for the privileged few. It was the lifeblood of the entire city, a physical expression of the common good. In an era of climate uncertainty and resource scarcity, these four principles form a powerful manifesto. Local materials, passive energy, radical durability, and equitable access. The Romans demonstrated that the highest form of engineering genius is not about dominating nature, but about creating a lasting, harmonious partnership with it. Their quiet stone channels challenge us to build a world not just for ourselves, but for the countless generations yet to come. The true marvel of the aqueducts was not the stone, but the symphony of skill that brought it to life. While we celebrate the names of Frontinus and Vitruvius, the reality is that their brilliant theories would have remained ink on parchment without the anonymous thousands who translated them into reality. These were the master engineers on the ground, the people who solved the daily puzzles of construction with an intuitive grasp of physics and materials. They directed the placement of each archstone, knowing its precise role in distributing weight, and supervised the mixing of that remarkable concrete, judging its consistency by feel and experience. Theirs was a knowledge earned not in libraries, but through a lifetime of observing how the world actually worked. The physical force behind this intellectual labor was a vast and diverse community. Roman legions, when not on campaign, were frequently deployed as construction corps, their military discipline perfectly suited to the massive, coordinated effort of moving earth and stone. Alongside them worked skilled freemen, stonemasons who could shape a block with breathtaking precision, and carpenters who built the intricate scaffolding and formwork. And there were countless others, including those performing essential daily tasks, who undertook the demanding work of excavation, hauling materials, and operating simple machines like treadwheel cranes. To stand at the base of an arcade like the Pont du Gard is to witness the culmination of this collective human endeavor. Every single stone was cut by a human hand, lifted by human strength, and set into place with human judgment. The sheer scale of the effort is almost incomprehensible, a monument not to a single emperor's vision, but to the coordinated work of an entire society. This quiet collaboration between the mind of the engineer and the strength of the laborer is the most enduring lesson of all. It reminds us that our greatest technological triumphs are never the product of a lone genius. They are always fundamentally a human achievement built by the many for the benefit of countless more. The Roman aqueduct stands not as a relic of a distant past, but as a living lesson in ingenuity, sustainability, and civic purpose.